Hello, Tanya Laird here, and welcome to part 1 of lecture 16 of ENGR 231 Engineering Statics. In this first portion of the lecture, we're going to be exploring some of the theory and formulas of area moments of inertia. So, much like centroids, this may be a review for some of you from previous physics material, and hopefully it is, so we'll be moving through this hopefully relatively quickly. Area moment of inertia. The area moment of inertia. So previously we have looked at centroids, and in turn the quantity, the first moment of area, came about. And this was our Qx and Qy. Or we refer to as Qx and Qy. So we remember that Qx, the moment of inertia, the first moment of area with respect to the x-axis, was equal to the integral of y dA, and then the first moment of area with respect to the y-axis was equal to the integral of x dA. And these were used to basically perform a weighted multiplier of the area of a shape versus its distance, or what I refer to as measuring how much area you have how far away from the x or the y-axis. And that's well enough, and that's good enough, or that's well enough. But here we're going to take this and go one step further. The area moment of inertia formulas are very similar, which is why I covered these in back-to-back lectures. The area moment of inertia, well, the formula is going to be fairly straightforward. Ix, which is the moment of inertia of a shape relative to the x-axis, is going to be just very much like this formula, except slightly modified. Instead of having a y term, this is going to have a y squared term. So we'll have y squared dA. And then Iy, the area moment of inertia, or what I'll refer to as simply the moment of inertia, is the integral of x squared dA. So basically the same formula, and not the same formula, but very similar formulas, and we will apply them in a very similar manner to how we solved for first moment of areas when solving for centroids. So what this will always come down to is that if we're doing this, there will be some exceptions, but generally if we have some curve here, if we're doing an integral with respect to x, we're going to have a vertical dA, and we'll have a dx here and some height here corresponding to the value of the function or the difference between functions, whatever it may be. And here you would have a function in terms of y rather than in terms of x. And if you had your function, then you would have let's say, or maybe I can show it something like this. You would have a horizontal differential element, but that horizontal differential element would correspond to a dy rather than a dx. Dy here, and then some sort of f as a function of y, and this would be some f as a function of x. Hopefully fairly straightforward. So what fundamentally does this represent, though? This is going to be a bit more important than, well, centroids are important as well, but the moment of inertia is a very fundamental quantity. And essentially what it is, you can read through more of the theory in your book, but the most important thing about area moment of inertia in terms of mechanical and civil engineering is that moment of inertia represents a cross-section's ability to resist bending. Equals a cross-section's ability to resist bending. And this is going to come up, especially when you look at higher level courses like mechanics and materials. When you apply forces, let's talk about this at a very high level, very upper level, not a high level, but a very general level. If you have a body or an object, or maybe even a member, at a general level, if you how members behave, how structural members and mechanical members behave, is that you will apply some sort of loads to this member, and that could be things like axial force, that could be moment, that could be shear, etc., whatever that may be, and then in turn you will get deformation. If you were talking axial force, Actually, if I'm going to use, I'll use the N for axial force because we looked at that previously, or we used that previously when looking at member internal forces. Deformation would be things like a change in length, they'd be a theta, a rotation angle, they'd be a strain, they'd be a shear strain, any number of things that you will see in mechanics of materials. So a member, basically, when you impose loads on it, exhibits some sort of behavior. The loads will be imposed on it. For example, if I am pulling on something, if I pull on something with a force of 5 kips, well, this would be tension or axial load, and it's going to undergo some change in, it's going to undergo some sort of deformation, and primarily it's going to undergo a strain, a change in length. So we could look at that in terms of delta x or epsilon strain. Again, I'm kind of getting into mechanics of materials here, but in terms of how much this thing actually stretches, there are two things that matter. The first one would be your modulus of elasticity, E. So the higher the modulus of elasticity, the less this thing is going to stretch. So if something like steel has a very high modulus of elasticity, so again, the higher the modulus of elasticity, the less this thing is going to stretch. And so if you have a material that is very strong, like steel, it has a very high modulus of elasticity. Something like clay or silly putty would have a very, very low modulus of elasticity. It does not have the ability to resist much force when loaded. And then the other factor is going to be a geometric property. For example, here, the geometric property would be the cross-sectional area. So if I wanted to predict how much this thing would stretch, if in a tension example, the modulus of elasticity is the relevant material property. So that will be a factor. So that is a material property. And then area is a cross-section property. So generally, and this kind of makes sense, the more area you have, if you have a giant beefy member, it's going to stretch less than a very tiny thin member under that same 5 kip load. But generally, two things of a member will determine its deformation relative to its loads, and that is its cross-section and its material. 1, the cross-section, and 2, the material. And in terms of bending, the relevant, and so basically backing up, for almost any one of these types of loads, there's a different cross-sectional property that's important and a different material property that's important. And for bending, the relevant cross-sectional property is moment of inertia. So for bending, the load you are placing on the thing, you are placing on the member, or you are imposing on member, is moment. Higher the moment, more bending. The higher the moments, the greater the bending. The greater the bending. The greater the bending. And then but again, talking about the relevant cross-sectional property, cross-section property, this is your moment of inertia, I. Your moment of inertia, I. Again, the moment of inertia fundamentally represents, now we can describe the mathematical formula for it, but when I think of moment of inertia, I fundamentally think of that number as describing a cross-section's ability to resist bending. So if you have something with if you have something like this, a small shape like this, and then another shape like this with a much larger moment of inertia, this shape is going to be able to resist a lot more bending than this will, and actually way more than this, the change in depth would indicate, because we have that x squared term in our integral, or actually y squared term for this particular one in that context. Again, so the higher the moment of inertia, the higher the moment of inertia, the greater the ability to resist bending. And fundamentally, this is what moment of inertia represents. And now, of course, we could talk about it in many different ways. But fundamentally, I think of when I think of moment of inertia, I think of that. I think of it as the ability of a cross-section to resist bending, or for a given material, for a given object, what function or not what function, what portion of its bending resistance will come from cross-section rather than, say, material properties. Okay, so there's that. And again, just like with another item I should probably mention, just as with QX and QY, IX and IY, in a way, sort of, measure the amount of area how far from the axis of rotation, or from the axis. From an axis. The difference, though, is that the distance is squared. However, this distance is squared. We have that x squared term in the formula, or the y squared term in the formula. And so, because of this, it is when you're designing shapes to resist bending, you try to get as much of your area as far from your centroid or your axis of rotation as possible. So in bending, you try to get as much area as far away from the centroid as possible, or from the axis of rotation as possible. Try to separate areas as much as possible. A shape's area as much as possible. And we'll see this when we get to the parallel axis theorem in the final lecture. Shape's area, try to separate a shape's area as far from the centroid, or maybe not separate, but position, as far from the centroid as possible. So think back to an I shape, or a wide flange shape. And hopefully now, if you think about this, you'll be able to realize the basic idea for why we build beams in this shape. Look at this. This shape is built to put as much of the area as far away from the centroid here as possible. Instead of having all of the area really close into the centroid, we have these big, huge plates far, far, far away from the centroid. And because this thing is always ends up bending about an axis like this. In simple elastic bending, you'll typically have bending about the centroid. And so the more area, and that would actually look more like this. These would actually be plates, not just line elements. And this would be these would be actual plates too. Something like this. But again, the basic idea here is to have as much of your area as far away from your centroid as possible, because that fundamentally is what creates bending resistance, at least in terms of material property. If I want to look at the formula for, say, bending stress, the bending stress formula, which is something we'll see in mechanics of materials, if you're not familiar with it, sigma is equal to mc divided by I. Now, C represents the distance from the centroid to the outermost fiber, so C for this one would be from here to the upper portion of this top flange, or the bottom portion of this bottom flange. And sigma is the stress that is built up in the material. The higher the stress, the lower the stress, the better. So it's going to be linearly proportional to moment, so the bigger the moment, the bigger the stress. But it is inversely proportional to the moment of inertia. So the more moment of inertia you have, the lower your bending stress. And we'll see this later on. Well, not in this course, but you'll see this when you get to mechanics of materials. Okay, and that really is the basic introduction to moment of inertia. There is another type of moment of inertia that you may have heard of course, and that is mass moment of inertia. This is slightly different. This occurs, or you'll see this a lot in dynamics courses. So often students, or fairly often students will take dynamics after statics. At least in our university, in the usual track for universities around here, students will take dynamics after statics. But for mass moment of inertia, it's similar, but basically I would say the moment of inertia mass is basically approximately equal to the integral of mr squared, or maybe dm r squared. You're basically doing an integral of masses and measuring how far squared they are from the from some axis of rotation. And where this is useful for is that this tells you the mass moment of inertia deals with rotation. Inertia, this effectively is what appears as mass in equations of rotational kinematics. Acts as mass in equations of kinematics or rotational kinematics. So it's important to not confuse these. These are both referred to as moments of inertia because they are calculated very similarly, but they are not the same thing. In equations of rotational kinematics. Acts as mass, again, in equations of rotational kinematics. Let's see. So, for example, if I wanted to show the, if I wanted to look at the acceleration that is present under a torque, I would say that torque, instead of saying F equals ma, which is the translational equivalent, I would say that torque equals I times alpha. I could say torque equals I times alpha. And really, these are just analogous things. Again, and also you'd see the same thing in equations such as delta x. This is a pure kinematics equation, 1/2 at squared plus v initial t. If you remember this from basic high school linear kinematics, you can also have something like delta theta is equal to 1/2 alpha. Well, actually, this is an example of moment of inertia appearing there, but you can also have things like say linear momentum, where you would have the linear momentum be equal to mass times velocity, and then you could have angular momentum, where this is equal to I omega. Your angular momentum is I omega. Basically, the equations for rotational and translational systems are the same in physics, or very similar. The only difference is that instead of having m, you will have I, and then the various analogous quantities, a and alpha, v and omega, but that of course is a bit outside of this class. So the important thing I just want to mention with this is that these are fundamentally different quantities. Don't confuse the two. One is your mass moment of inertia deals with the distribution of mass across a three-dimensional object, and the area moment of inertia deals with the distribution of area within a cross section. So both have their uses. Both are very useful for practicing engineers and engineering students, but it's important to not confuse the two. All right, that'll serve as a brief introduction to moment of inertia. In part 2 of this lecture, we are going to look at how to calculate some basic moments of inertia for some simple shapes. All right, please let me know if you have any questions. Again, this is just a basic introduction to moments of inertia. Hope you found this interesting and fairly easy to follow, and hopefully not too bad. And I don't think this was too bad. So again, please let me know if you have any questions. If not, I'll see you soon for part 2. And as always, thank you.